Hi everyone, welcome to my channel Dr. Sidhu Physics Tutorial. In this session we are going to discuss the new concept electric field lines, which are also known as lines of electric force. What are the electric field lines? In general, in any region the electric field can be visualized by drawing some imaginary curves. Those imaginary curves are called electric field lines. But what is the direction of the electric field in that region? By drawing the tangent at any point on those curves gives the direction of the electric field. Figure A and figure B represents the patterns of electric lines of forces which are formed by the positive charge and negative charge. By observing the figure A, the electric lines of forces which are diverging out from the positive charge and which are converges into the negative charge. In figure C, there are two charges of same nature. That means these two charges are positive nature, having positive nature. That's why the electric field lines are repelled to each other. They are away from the positive charges. In figure D, there are 2 point charges. One is positive charge, another one is negative charge. The field lines are attracted to each other. That's why the field lines are starting from the positive charge and ends on the negative charge. In figure F, as the size of the point charges increases, the curving nature of the electric field lines decreases. In figure G, there are two rods with positive charge and negative charge. The electric field lines are in between them is parallel to each other and also equidistant from each other. Let us examine the properties of the electric field lines. As we discussed earlier, all field lines diverge out from the positive charge and converge into the negative charge. Next property of the field is the tangent to the field line at any point gives the direction of the electric field. The third important property is, in nature no two electric field lines intersect each other. If they intersect at a point, at that point the field should have two different directions, which is not possible in nature. The field should have only one direction. If they intersect to each other, the field should have two different directions. That's why, which is not possible in nature, any two electric field lines cannot intersect each other. Next, fourth property is the field lines are always normal to the surface of the conductor. That is, the field lines are perpendicular to the surface of the conductor. Fifth property is electric field lines do not pass through the conductor. That means the electric fields are not able to pass into the conductor. The sixth property is electric field lines are open lines. They start from positive charge and end on negative charge. That means as the electric field lines are do not pass through the conductor, that's why they cannot form the closed loops. Only they start from the positive charge and end on the negative charge. If the field lines are crowded, the field is strong, and they are sparse where the field is weak. If the field is strong, the electric field lines are very close to each other. That means crowded. If the field is weak, the electric field lines are away from each other. That means sparse. The eighth property of the electric field lines is, in charge-free region, electric field lines are continuous curves without any breaks. That means if the field is created by some charge, the electric field lines are continuous up to infinity until we should place the another positive charge in the vicinity of the positive charge. Ninth property is electric lines do not form any closed loops. This indicates the conservative nature of the electric field. If any force is said to be conservative, the work done by the force should be stored as a potential energy in that body. That's why that force is called conservative force. That force created by the field is called conservative field. Here electric field is conservative in nature. Types of electric fields. In nature there are two types of electric fields. First one, uniform electric field. Second one, non-uniform electric field. Uniform electric field, the field in which at every point the intensity of electric field is same both in magnitude and direction. Example, electric field between the plates of a parallel plate capacitor. As we seen in the example figure G, if there are two rods with positive charge and negative charge, the field lines are parallel to each other in between these two rods. This is the best example for the uniform electric field. Non-uniform electric field, the electric field in which the intensity of electric field is changes from point to point either in magnitude or in direction or in the both. For example, electric field due to a point charge. Due to the point charge, the electric field can be formed by the lines which are diverging out from the positive charge. At any point on these lines, the field direction is different for different lines. That's why the electric field due to a point charge is non-uniform electric field in nature. Next topic is electric field. The space around any electric charge where its influence can be felt by another charge is called electric field. Consider a point charge which is placed in a space around which an electric field will be produced. If you place another charge in the vicinity of the point charge, that point charge may be attractive or repulsive. That means the force created by the electric field can be felt by the another charge. That means some electric field is there. But what is the magnitude of the electric field act on that particle? That means that is also called intensity of electric field. The electric force experienced by a unit positive test charge is called intensity of electric field E. Intensity of electric field E equal to F bar by Q naught, where F equal to electrostatic force between the charge and the positive test charge. It is a vector quantity. That means it has both magnitude and direction. What is the direction of the E bar? The direction of the field is along the electric force if the charge is positive. The direction of the field is opposite to the electric force if the charge is negative. The units of the electric field intensity is given by the Newton per Coulomb. Let us draw the mathematical expression for the intensity of electric field. Consider a charge capital Q which is placed at a point A in the space. Then there will be some electric field around the Q. If we want to place a unit test positive charge Q naught at point B which is at a distance smaller from A, then the force of attraction or repulsion between the Q and Q naught is given by the Coulomb's law, F equal to 1 by 4 pi epsilon naught into Q naught by R square, which is the force of attraction or repulsion between the Q and Q naught. But according to the definition of the intensity of the electric field or electric field induction, E bar equal to F by Q naught. If you substitute the F value in this equation, we get the 1 by 4 pi epsilon naught Q naught by R square into 1 by Q naught get cancelled. We get the E bar equal to 1 by 4 pi epsilon naught Q by R square, which is the expression for the intensity of the electric field at a point in a electric field region. In order to understand this concept, let us do some example problems. First problem. The force experienced by a charge of 2 microcoulomb in an electric field is 3 into 10 to the power of minus 3 newtons. The intensity of the electric field is, here our aim is to calculate the intensity of the electric field. Let us go for solution. And the given conditions are force F equal to 3 into 10 to the power of minus 3 newtons, and also charge is also given. Charge Q equal to Q mu C. Here mu means micro, that equal to 10 power minus 6 coulombs. Here E equal to question mark, that means we have to find the intensity of the electric field. Therefore, according to the definition of the intensity of the electric field, E equal to F by Q. Here F equal to 3 into 10 to the power of minus 3 and Q equal to 2 into 10 to the power of minus 6. 3 by 2 implies 1.5, and if you bring the minus 6, 10 to the power of minus 6 to the upwards, it becomes positive 10 power minus 3 into 10 power 6. As the bases are equal, the powers will be added, that means 6 minus 3, that equal to 10 to the power of 3. Therefore, E equal to 1.5 into 10 to the power of 3 Newton per coulomb, which is our required answer in options. Option 1 is the correct one. Next one, A and B are 2 points separated by a distance 5 centimeters. Two charges 10 microcoulombs and 20 microcoulombs are placed at A and B. The resultant electric intensity at a point P outside the charges at a distance 5 centimeters from the 10 microcoulombs is given by. Here the conditions are, there are 2 points A and B which are separated by a distance 5 centimeters. At A we place the 10 microcoulomb, at B we have to place the 20 microcoulomb charges. Here the point P lies 5 centimeters from the 10 microcoulombs. Then we have to find the resultant electric intensity at P. Due to the charge at A, that is 10 microcoulombs, the intensity of electric field is in the direction of E1 as shown in the figure. That means Q1 is a positive charge, that means the electric field lines are away from the charge Q1, that means Q1. Again, due to Q, the electric field is also away from Q, that means that is given by the direction E2. Here E1 and E2 are in the same direction, that's why the net electric field at point P is given by the sum of E1 and E2. Let us find the individual electric field intensities. E1 equal to 1 by 4 pi epsilon naught into Q by R square, where Q equal to 10 microcoulombs and R is the distance between the Q1 and point P, that is 5 centimeters. Centimeters can be converted into meters, that means 5 into 10 to the power of minus 2 whole square. The value will be, the 1 by 4 pi epsilon naught value is 9 into 10 to the power of 9, and 10 into 10 power minus 6 by 5 square means 25 into 10 power minus 2 whole square means 10 power minus 4. 5 2s and 5 5s, we get the 18 by 5 into 10 to the power of 3 into 10 to the power of 4. The resultant is 3.6 into 10 to the power of 7 Newton per Coulomb. In similar manner, we should calculate the E2. 1 by 4 pi epsilon naught into Q2 by R square. Here the distance is 5 centimeters plus 5 centimeters. The point lies at a distance from the Q2 is 5 centimeters plus 5 centimeters, that equal to 10 centimeters. That means 10 into 10 to the power of minus 2 whole square. Finally, we get the E2 as 1.8 into 10 to the power of 7 Newton per Coulomb. But what is the net electric field at P is given by the E1 plus E2. Why? The electric field due to Q1 is in the direction of the electric field due to Q2. Both are in the same direction. That's why we have to add the two field intensities. That's why E net equal to E1 plus E2. The answer will be 54.10 power 6 Newton per Coulomb. What is the direction of the net electric field? It is away from these two given two charges. So option 1 is the correct. Problem is at the corners of A, B, C of a square ABCD, the charges are 10 millicoulombs, minus 20 millicoulombs and 10 millicoulombs are placed. The electric intensity at the center of the square to become 0, the charge to be placed at the corner D is. In this situation, there is a square A, B, C, D. At A, we placed a 10 millicoulombs and at B, we placed a minus 20 millicoulombs. At C, 10 millicoulombs. At D, there is no charge. We have to place some charge at D. Due to this charge, the electric field at the center of the square must be 0. Here, the electric field due to the charge at A is directed towards the center O, that is indicated by the letter EA in the diagram. Due to the charge at B, because of this is a negative charge, that's why the electric field is towards the charge, as we discussed earlier in the concept. Electric field is opposite to the force of the charge if it is a negative. So EB acts towards the B. Due to the charge at C, it is a positive charge. That's why the electric field is away from the charge. That means it acts towards the center of the square. Here we observe the EA and EC are opposite to each other and also equal in magnitude. That's why they are cancelled together. That means EA and EC are cancelled together. To cancel the EB, the direction of the ED should be opposite to each other and also it is same in the magnitude. That's why at the corner D, we have to place the minus 20 millicoulombs. The charges are, the electric field produced by the charges must be in opposite directions. That's why they are also cancelled together by resulting the 0 electric field intensity at the center of the square. So our option is minus 20 millicoulombs. We have to place at the corner at D in order to the resulting electric field at the center becomes 0. Next question. A charged oil drop is suspended in a uniform electric field of 3 into 10 to the power of 4 volt per meter so that it neither falls or rises. The charge on the drop will be. Take the mass of the charge. 9.9 into 10 to the power of minus 15 kg and G equal to 10 meter per second square. Here the given conditions are, here electric field E equal to 3 into 10 to the power of minus 4 volt per meter, and also mass of the charge M equal to 9.9 into 10 to the power of minus 15 kg, and also acceleration due to gravity G equal to 10 meter per second square. We know that intensity of electric field E equal to F by Q. Here drop is neither falls nor rises. That means the weight of the body must be equal to electric force. That's why here F is the electric force. In the place of electric force we should include the weight of the charge, that means mg. Therefore mg by q. Therefore E equal to mg by q. Our aim is to calculate the charge on the particle. Therefore q equal to mg by E. By substituting the mass m and g electric field in that equation, we get the 3.3 into 10 to the power of minus 18 coulombs, which is our required answer. Option 1 is the correct one. If you like this video, please like, share and subscribe my channel.